Okay, now here, as I record this video, we're coming up on the time of year when the Nobel Prizes are going to be announced for 2024. And I kept looking at the people are in the mix going, wow, there's some really cool stuff here. But then I come across the 1926 Nobel Prize in Physics, which is this particular video, and I actually didn't know a lot about this man before doing a little bit of research here. So the prize winner that year was Jean Baptiste Perrin. He won for his work in the discontinuous structure of matter and especially for his discovery of sedimentation equilibrium. Now that's a whole lot of scientific gobbledygook, but let's go make sense out of it. First, let's understand what sedimentation is. It's the process of particles in something. So sedimentation can be thought of as particles settling at the bottom of a body of water, or at the bottom of a wine glass, or at the bottom of anything. Lakes, rivers, all kinds of places. This can occur in any liquid. You don't want sediment to gather in one spot. You want it to be at equilibrium throughout the body of water, the body of liquid. You don't want it all clumped at the bottom. You don't want it all clumped at the top. You want it kind of uniform throughout. When it is uniform throughout, that's what we refer to as sedimentation equilibrium. Now, he was studying this sedimentation process by using Brownian motion, which we've discussed in other Nobel Prizes, because it turns out to be a very useful phenomena. Brownian motion is sort of the random motion of particles suspended in some kind of a liquid or a gas. So you sprinkle something in and they tend to move around. So picture a water glass, if you will. You pour some salt or sugar or something into it, and it kind of randomly continues to move. One of the other Nobel Prizes was looking at the effect of pollen on the top of liquid. It never seems to stand still. He was using this for a different task. And what he did was he absolutely nailed down and solidified all kinds of things by this study. So what kind of stuff did he nail down for us? This was further proof in this set of experiments of the absolute atomic nature of all matter. There was still some questions about different things at this period of time, because remember, his work was done in 1895, so it wasn't like this was done yesterday. And some people were still kind of questioning that atomic nature of everything, and how are we made out of the same stuff that the sun is made out of, the trees are made out of? How is that possible? We're obviously different. Well, true, but the atomic structure is different. The atoms are the same. He also used his studies to determine Avagos constant by this and several other methods. He also explained a couple of other things that we'll get to in a second, but let's try to figure out what is that Avagos constant thing. You may have heard of that before, and it turns out to be relatively important. Avogadro's number is basically just a way for scientists to kind of communicate. It permits somebody to compare how many atoms or molecules are in a given substance with somebody else. So if you're in a lab doing a large chemistry experiment, you want to understand, hey, I'm going to mix this much hydrogen with this much oxygen. The chemical formula is H2O. If I really want to get water and do it efficiently, I have to have twice as many moles of one as I have of the other. This is essentially how you get to moles of a substance. It's just a fancy way of saying how many of something are in there. So it's a great way for scientists to communicate, because if we're all talking different things, whether that's centimeters to inches, we need to understand that, and those numbers become very important. Because otherwise you may wind up with, you're trying to form water and say, well, okay, I'll just use a whole lot of hydrogen. Great, I've got 3 times as much hydrogen as I have oxygen, and I got a great mix, and I have this one hydrogen atom left over, but who cares? It's just hydrogen. It'll float away. And the only trouble is hydrogen is very volatile, and it could explode on its way out of the reaction chamber, so you want to be careful. You want to make sure that you don't have too much of something when you're trying to do a particular set of scientific experiments. And this is a fantastic way to do that. We also have him to thank for being the first person to explain that what goes on in the sun is actually a nuclear reaction of hydrogen. So lots of people were kind of still mystified as to what exactly was going on in the sun. They knew it was there, they knew it was a star, but they didn't understand the actual process. So he was the first to really explain what was going on in there. And if you look at the wording of his prize, it wasn't for one particular thing. It was for a lot of contributions to the field over the years. So the wording was for his work on the discontinuous structure of matter, and especially his discovery of sedimentation equilibrium. And that sedimentation equilibrium allowed him to do all that other work that he gave us, so that other scientists could go off and do things in the future. he is one of those people that when you hear the phrase "on the shoulders of giants," he is one of those people we really are standing on the shoulders of, because his work allowed other people to come along and do things that may be a little bit more practical in a sense from an engineering standpoint, but without his work we wouldn't be able to do those other far more practical things. So he gave scientists a lot of, hey, look, it really is atoms. We're really not making that up. Here's how they all work. The sun is just a big ball of hydrogen undergoing nuclear reactions. And here's this Avogadro's number, so you can all be speaking the same language. And there's a lot of science that went into why Avogadro's number is exactly the way it is, which we'll save that for another video. But this man we have to thank for a lot of his just tying together a lot of loose pieces that existed in science at this point. And now it kind of all makes sense. Well, yeah, it's obvious those all fit together. But when he did his work, he didn't know that. He's the reason all those things really seem to fit together all that well. So I hope everybody has enjoyed this video. A lot more Nobel Prizes in physics to go, and then we still have chemistry and other fields. Please click subscribe on the channel if you haven't already, and we will see you on the next video.